Once again, hello and welcome back. I would like to introduce Dr. Daniel Yeager. Dr. Yeager is a spectral imagery scientist with the Department of Defense. His research focuses on multi and hyperspectral imagery analysis, environmental remote sensing, and field campaign work. Additionally, he has supported numerous educational outreach efforts focused on imagery science careers. Dr. Yeager received his PhD in atmospheric science from Howard University, where he studied the effects of Saharan dust plumes on regional climate in the tropical Atlantic. Daniel will be teaching us today about monitoring methane point sources with commercial and civil satellite imagery data. Thank you very much for being here.
Thank you. All right, let's see here. So good morning, everyone. I'm Dr. Daniel Yeager again, and as she mentioned, I'm a spectral imagery scientist at the Department of Defense. From a technical standpoint, I've focused on spectral imagery analysis of commercial satellite sensors to support a lot of regional and global intelligence issues. Prior to my time here, I did receive my PhD again in atmospheric science from Howard University with the focus on environmental remote sensing, aerosol measurements, and field campaigns. So today I'll use some of that background to discuss some preliminary assessments of ways we can monitor point sources of methane emissions using commercial and civil satellite sensor data. Next slide. Okay, so methane is a powerful greenhouse gas responsible for a significant fraction of Earth's global warming since the industrialization era. And studies are showing that it is still increasing on a global level per year. So it's primarily emitted from a variety of man-made and natural sources that include the coal, natural gas, and oil industries, as well as agricultural, livestock, and also waste treatment practices. So it has a relatively, I guess, short atmospheric lifetime in compared to, like, say, CO2, with the trade-off of having much longer, or much larger, rather, global warming potential compared to CO2. So because of those factors, there's a lot of, I guess, potential for global warming mitigation through addressing methane contributions from the fossil fuel industries. In addition, there's also a growing need to monitor these methane leaks from these fossil fuel industries at facility level scales. Next slide. So over the years, there has been an explosion of, I guess, greenhouse gas monitoring satellite systems with methane detection capabilities, some of which can monitor actual point sources of methane leaks from fossil fuel facilities. So here I'm kind of briefly and at a high level just highlighting some recent and emerging satellite sensors with methane monitoring potential. We see at coarser spatial resolutions, there are sensors data such as tropomy, and when we go up to, say, moderate resolution, which is like that sub-kilometer scale, but say greater than about 50 meters in pixel resolution, you've got things like GHG-SAT and Methane SAT that are coming online. And then if you go a bit higher in resolution, in that 3 to 30 meter pixel category, there's a lot of new data that's sort of being tested related to Prisma sensors, Sentinel-2, Worldview 3, and in the future, Carbon Mapper coming online, I believe, very soon. So when we look at the high resolution category, some of the sensors of interest for this study included Landsat 8, Sentinel-2A particularly, and Worldview 3, which provide respectively 30 meter, 20 meter, and 3 to 4 meter spatial resolution for methane detection capabilities. So there's quite a bit of, I guess, utilities out there, and it just depends on what sort of range of spatial and spectral capability you want to monitor these different plume emissions. Next slide. So This work has three main objectives. The first was to evaluate multi-band shortwave infrared methane retrieval techniques for methane leaks of oil and, or I guess, oil field facilities. And again, we're focusing in this study at this phase on Sentinel-2, Landsat, and Worldview 3 data. The second bullet there, we're really just trying to provide a proof of concept of established retrieval techniques over a variety of sceneries, point source emission rates, and overhead systems. And finally, we want to identify future developmental needs of methane retrievals using high resolution overhead systems. All right, next slide. So I want to give kind of a quick overview on the methane retrieval techniques we applied during this, this study for these commercial and civil systems. Basically, to give a little bit of background, again, methane gas is a good absorber of shortwave infrared radiation, particularly at the 1600 and 2300 nanometer range. It has a very strong absorption feature in the 2300 nanometer range and a weaker one in the 1600 nanometer range, as shown in the figure above on the top right there. So the general idea about that is that it has these absorption features, and then it also has good spectral bandpass. Some of these sensors have good spectral bandpass overlap with those absorption features. So for this work, we evaluated a two-band methane retrieval approach near and adjacent to those strong absorption features near 2300 nanometers. And again, we focused on the Sentinel-2, Landsat, and Worldview 3 data sets. So the general principle behind this retrieval is that there's a measurable fractional change in the top of atmosphere reflectance received by a given sensor due to methane between the strong and weak absorption bands. And this can be described in equation 1 there, where our R sub S is our strong absorption band and R sub W is our weak absorption band. And C is some scaling factor to adjust for the interband scenery and viewing geometry differences. So we can then model these fractional changes using radiative transfer models such as Montran, as shown in equation 2, where T is our sensor radiance for strong and weak absorption bands under assumptions of background and enhanced total column methane concentrations. So for this study, we modeled the sensor radiance under a range of total column methane concentrations, and we relate that to the observed sensor radiance to determine column methane concentration enhancements, as shown in equations 3 and 4, where in this case, our delta X in equation 4 represents the total column methane enhancements. So that's a little background about how our two-band retrieval is working. Next slide. So the main workflow I implemented to carry out some of our research objectives was basically, first, we start in that top left block there, where we're trying to acquire suitable SWIR imagery or shortwave infrared imagery. That sounds simple, but it was actually more challenging because methane gas leaks are so intermittent and variable in intensity. So just because you're at an oil field facility doesn't mean you're going to just readily observe some of those super emitter methane gas leaks that we sometimes see. So there was a little bit of challenge there, but we did focus on the Hassan Masoud, I might have pronounced that wrong, oil field in Algeria, and also the Korpesi oil and gas field in Turkmenistan. So we do some basic imagery processing and metadata extraction using Python GDAL, and we model the sensor radiances under viewing geometry and scenery conditions at the time of overpass. Basically that delta M that I showed in the previous slide. So for our fourth block there, we use that information to compute the total column methane concentrations. And then eventually, but not shown in this work, we're going to be computing what we call integrated mass enhancements of methane plumes. Basically, how many kilograms per hour do we observe for an identified methane plume? So that's just a kind of a general overview of the workflow. Next slide. So I've talked a bit about modeling that sensor radiance, and here's a little more detail to speak to that. So we show some results of in this image on the right here, we're showing, or figure on the right here, we're showing some results of sensitivity studies for Landsat, Sentinel-2, and Worldview using our 2-band methane retrieval approach highlighted in the study. So the plot on the right really shows the radiance percentage differences as a function of methane concentrations that each sensor has. And for this example, we're assuming that we're at nadir, or looking directly down at our target, and we're about 40 degrees for our solar zenith angle. And for these different sensors, for Worldview 3, Sentinel-2, and Landsat 8, we have a lot of discrepancies in how much radiance sensitivity they have. So for Worldview 3, with its higher spectral resolution, we see that a doubling of methane concentrations equates to nearly an 11% difference in sensor radiance, whereas for the the Sentinel-2 and the Landsat 8, we're closer to like a 3% sort of sensitivity rate for that for those sensors. So for Landsat 8, there's actually a slight advantage over Sentinel-2 as far as sensitivity. It's like at 3.1% versus 3% for a doubling of methane concentrations, all other things being equal. But clearly Worldview 3 has the advantage when it comes purely to spectral sensitivity to methane column enhancements. But it is important to note that while Worldview 3 does have superior detection capabilities, it has some trade-offs because it's not as easy to acquire the data and get consistent revisits over sites of interest. And that's where other sensors like Sentinel-2 can provide consistent 2 to 3 day revisit times for different facilities and sites of interest as it relates to methane emissions. Landsat 8 and 9, which has come online, will offer a total, I guess, about 8-day revisit cycle. So yeah, just a little bit of background about how sensitive these different sensors are to methane column enhancements. Next slide. So I'm going to show some of the preliminary analysis that we've done for methane retrievals on the Landsat, Sentinel-2, and Worldview 3 sensors. Starting off with Landsat 8, here you can see some of our results from our 2-band retrieval techniques over an active methane leak in the Hassan Messaoui oil field in the deserts of Algeria. This image was acquired on November 17th, 2020, and it's very near to an active well pad in the, again, in that oil field region in Algeria, where there's actually been a lot of recent literature put out on methane leaks and monitoring that with different civil sensors. So this particular plume appears to be about several kilometers in swath and has, I would say, based on preliminary assessments, 1 to 3 times the background concentrations of methane if we assume them to be at about 18 to 1900 or so in background concentrations. So we're seeing values roughly from, like, say, almost 2000 to around 5,000-ish parts per billion for this particular plume on this particular day. You also note that the plume is quite wispy. There's a lot of gaps in our retrieval, which may be accentuated by the coarser 30-meter pixel resolution for Landsat 8 sensors, as well as some of the surface background interferences underneath the plume. But just a exemplar sort of image of retrievals we can do with the Landsat 8 data. Next slide. So here we have a Sentinel-2A shot of nearby, or actually still the same region in Algeria. And it's also, well, in this case, it was collected in November, but November 20th of 2019. And for this image, we see much more defined methane plumes originating from this facility in the center of our image. And if you look really closely, you can actually see what appears to be some fuel storage tanks in the center of the image there, and our plume is kind of wafting out to the left or to the west of that facility in the middle there. So the plume is of comparable size to our last image, where it's on the order of several kilometers, but it also has, in addition to that, it has very similar ranges in methane concentrations to the prior image, which is roughly 1 to 3 times the background concentration. So we're again around that range between, say, 18 or 1900 to as much as 5,000 parts per billion for this particular site for methane concentrations. So while we did see similar spatial and concentration ranges in methane plumes as the previous image, in this case, it does appear that the 20-meter resolution of the Sentinel-2 provided a much more spatially resolved and identifiable methane plume for point source emissions. Next slide. All right, so moving on to Worldview 3, or kind of going up in resolution again. Here we implemented that same 2-band retrieval. However, we looked at the Korpezi oil and gas field of Turkmenistan, and this shot was taken on April 10th of 2021. And in this case, our plume is significantly smaller. It's actually more like 1 kilometer in length, and it's clearly originating from a point source in the right of our image. So for this plume, we saw that there were much higher methane concentrations, about 4 times the background, and as much as maybe 7,000 parts per billion near the point source there. But as the plume sort of wafted off to the west there, we saw that the concentrations dropped off considerably to 1 to 3 times the background concentration. So you can see here clearly that the higher spatial and spectral resolution of the Worldview 3 shot allowed for nicely resolved plumes at very fine sub-kilometer scales here for Worldview 3. Next slide. So there's quite a bit of future work here ahead of us. For one, we're looking at optimizing our methane retrievals, specifically coming up with more robust in-scene surface characterization methods to reduce some of those false alarm rates in the methane detections. We're really interested in exploring different plume modeling techniques available to estimate emission rates, particularly getting to that kilograms per hour sort of terminology versus concentrations like we've mentioned in the slides. And as I mentioned for, or I guess the third bullet there, we want to kind of take into account the fact that methane leaks are highly variable and not well reported. And so, having access to any data that provides more ground truth and controlled emissions types campaigns really would help to validate some of our SWIR retrieval efforts. And lastly, we want to expand our retrievals to some of the emerging sensors talked about earlier. Next slide. So just to recap, our preliminary work implemented 2-band methane retrievals and showcased the capability of land imaging sensors to detect and quantify point source emissions of methane leaks at sub-kilometer scales. We did link these facility level super emitter events and regional global emission trends to help us understand some of the disproportionate contributions of super emitter events on global emission budgets. And finally, we feel that there are a lot of emerging methane sensors, as well as existing land imaging sensors that can be repurposed for methane retrievals. And overall, this will provide greater international inventory assessments and situational reporting. So next slide. This concludes my presentation. I'd like to thank L3 Harris for the invitation, and I open things up for any questions. Thank you.
There we go. Thank you very much, Daniel. We got a lot of questions. I'm only going to do one, but if you guys have questions, please feel free to send them directly to the person or start a conversation, whatever you like. So uh, one of the questions is, how specific is that multispectral algorithm to methane? That is, if you didn't know that was an oil field, would you still be able to interpret that signal as methane?
Um, it is very specific to methane because the regions that we're looking in, they don't have a lot of interfering gases, for one. You don't have interference from, if you had a high amount of water vapor, it would make a very, I guess, non-significant impact on the spectral signal. And the same is true for CO2. So you don't have a lot of interference from competing gases in this particular region. And it really comes down to good characterizations of your surface features. And in this case, you can really identify methane because it looks like a plume. And if it looks like a plume, that's already going to give you more confidence versus if it has more geometric shape to it and resembles, say, surface features. But that is an area we're addressing right now.
Fantastic. Thank you very much. Yeah, like I said, unfortunately, we're only going to have that as the one question. If you have follow-up questions, feel free to submit them directly to the speaker, because there were quite a few that started popping in there. Once again, when we close this session, you have a few minutes to get to the next session. Just click back to that main homepage where you have your upcoming meetings listed and click on the next session to join.